Hello.
நாக்காடு வந்துட்டு
Hello, Mr. Kadaksabai. Hello.
good evening.
Good evening. Good evening.
Hello.
Yes, good evening. Nimesh ji is joining, no?
Dimesh is not joining. Saurabh Sharma is there from
Okay.
Sigma Weld. He will present the presentation for the Sigma Weld.
Okay.
Now, Dr. Krishna introduce.
Dr. Krishnan is there.
Yeah.
Okay.
Good afternoon, Graham, and good afternoon, Judge.
Well, good evening, actually.
Yeah. So you have joined from Australia today?
That's correct, yes.
Yeah. So it's an
10:30 in the evening.
Yeah, what is the time there now, local time?
about 10:30 in the evening.
Oh, okay. Okay.
That's all right. I'm used to your Saturday meetings.
Great. So, Graham, we will start in another 7 minutes.
Yep. Okay.
Yeah.
Good morning, Graham. Gary. Hey, Gary. Hi. Evening,
Good
Graham.
morning.
Good morning, Gary.
Yeah, good morning. It's early.
Hello, sir. How are you? Gary, sir?
Yeah, how are you?
I'm fine, sir. How about you?
Oh, okay. It's early morning here. I got my first coffee, so
That's okay.
yeah, looking forward to the day.
Mhm.
Good afternoon, Jug.
Hey, good afternoon, Krishnan. How is life?
Yeah, all well, all well.
I
So
have not forgotten about you, but
Yeah.
as you know, it's sometimes difficult to get feedbacks out of India.
I know. Rohit is uncatchable.
Yes, that's true.
Let
But
us
we
hope
will
for
get
the
there.
best.
Because, we did it I think it's 2 years ago.
Yeah, you did. Yeah, exactly 2 years ago, it was
Yeah.
sponsored. Yeah.
Yes, correct. And I want to do it the same way
Yeah, right.
because that's the easiest way.
Yeah.
That sounds very cryptic.
Yeah, this is insider trade. Hmm.
I'm sure Moscow knows all about it.
Yeah, that's why we
And
said
we are
it.
being recorded.
Yes.
Good.
So again,
afternoon. Good.
today again we have almost 700 registrations. So I hope around 200 might turn around.
Great.
Yeah.
That would be fantastic. We heard, Graham and I heard that you had over 700 registrations.
Yeah.
80 had joined, still 3 minutes or more. Let us check. Dr. Krishnan, Nimesh is joining.
Okay.
Within 2-3 minutes, he will join and he will present for the presentation.
Yeah.
So what is the weather like in Mumbai?
It's not too cold. I mean, around 24, 25.
Ah, okay.
Very comfortable.
It's a very pleasant weather now.
Yeah. Well, it's actually not too cold here. It's +2 degrees. So but we're expecting
Canadian
like
summer.
minus 17, 18 next week. So
So you are in Canada, right, Gary?
right.
Yeah.
Yeah. No. Even in the US, they'll get this, we call it a polar vortex, but Mr. Trump's inauguration, they've had to move inside because it's too cold outside to have it. So next week on Monday, yeah.
So how
Wouldn't
is
have happened
Singapore,
to a
sir?
nicer person.
How about Singapore?
That one is always the same. At the moment, I would suggest it's some 20, 26, 27.
Okay.
We've cracked 100.
Yeah, it's already 100 plus.
So Jay, what we will do is Nimesh will present about his company being the sponsor. Yeah.
Yep.
Then I will introduce you. Then you take over and then introduce the speaker.
Absolutely, we do it this way. Yes.
Yeah.
It looks like Jörg is also waking up.
Going to bed soon. Again.
It's early for a Saturday night.
Yeah.
Yes.
So generally, people from almost 20 to 24 countries attend this talk.
It's fantastic.
Yeah.
God.
So you are all known in almost, all these 24 countries.
It's all right.
Yeah.
But would be interesting to have afterwards a summary of the countries, because I always write a short report, and we have another one due soon, and telling them what kind of exposure we get through you, that would really help.
Yeah, we will do that. In fact, some point in time, we should plan a physical one, in India.
Yeah.
Oh, always in. Haven't been to Mumbai for a long time. Would love to come.
I think we will plan that.
Good.
I just noticed in the chat that somebody from Senegal is on the line. So that's that shows the widespread
Amazing.
influence you have.
Okay. So that is, I think, the 25th country then.
Yeah.
Saudi.
Yeah, there's Saudi.
Sachin, are we good to start?
I would say so, yes.
150-ish.
Yeah. Sachin?
There's Bahrain.
I think Sachin is the host. Sachin?
I think he is waiting for Nimesh or his company.
I
Or
think
he is talking.
Saurabh is from Sigma, right? Saurabh Sharma.
Yeah.
Saurabh.
Saurabh is trying for Nimesh. He's talking with him. Let me check 1 minute.
I think we should start now.
Yeah, just wait for 1 minute. Let me check with Saurabh again because he's talking with Nimesh.
Uh-huh.
Nimesh. Yeah, good evening, Nimesh.
Good evening, good evening.
You writes to you, just a minute.
Yeah, so
Nimesh here. Krishnan Saab, how are you?
yeah, good, good. So we all of us are ready. I think we can start.
Waiting to Nimesh to start.
Saurabh Sharma again. Saurabh
Okay.
Sharma.
Is Vikram there or Saurabh there from my team?
Yeah, you're from joined from Saurabh Sharma, no? Two Saurabh
Saurabh is,
Sharma.
yeah, Saurabh. I can see Saurabh in the panel.
Okay. Saurabh can share the video. So once I will just welcome everyone. Good evening. How are you, Gary? Mr. Graham, how are you?
Fine, thank you.
Good evening from Middle East. Today I'm in Dubai.
Hello, Saurabh. 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 हेलो सौरभ निमेश जी आपको राइट्स दिया मैंने किसको राइट दिया
So, very quickly, good evening all. I'm Nimesh Shenoy from Sigma Weld. And I think we've taken a little bit of time. If my team can play the video, good. Otherwise, you guys can continue. Warm welcome again to Dr. Graham Sussex for another interesting talk on Duplex. And Dr. Krishnan, maybe you can introduce Dr. Graham and then we can start it further.
Yeah, yeah. Thanks, Nimesh. I will introduce Jerk first. Yeah.
Sure.
So good evening, everyone, for an interesting talk today on welding of duplex and super duplex, the practical aspects. So let me introduce Mr. Jerk. Mr. Jerk is the market development manager, Southeast Asia for the Nickel Institute, and he is based in Singapore. Mr. Jerk is responsible for market development activities in Asian market outside Japan and China, executing projects, developing opportunities, and managing partner relations in the region. So he is very familiar to us, and Mr. Graham and Mr. Gary is also in the panel today. So we welcome you all. And now I request Mr. Jerk to introduce the speaker.
Okay, thank you very much, Krishnan, for the kind words. If I can share my screen, that would be fantastic. That would mean the host has to give me the right to share.
Saurav, you will have to transfer the rights.
नंबर तो नहीं है आपका
Jerk, you have the rights now.
Okay, yes, I saw it. Yep, thank you very much. And share. So hope everybody can see it. So let's go into it. The Nickel Institute is a global association of the leading nickel producers promoting the proper use of nickel in various applications, as we will hear as well throughout this webinar. We support markets for new and existing nickel uses, including stainless steel, by advocating for sound science, risk and management, and socio-economic benefits in public policy and regulations. Nickel plays a vital role in over 75% of stainless steel, providing the exceptional physical and mechanical properties. These qualities make stainless steel durable, versatile, and easy to use in numerous applications. Our headquarters the headquarters is located in Toronto, whereas our science division, NIPERA, is in Durham, the US. In Brussels is our European Center of Excellence for Public Policy and Sustainability, Communication and Market Development. 2 subsidiaries are located in Brisbane and Singapore, and the offices in China and Japan are taking care of the respective countries and are non-government organizations. The International Molybdenum Association, in short, IMOA, is a global non-profit trade organization like the Nickel Institute and representing most of the molybdenum industry. It promotes the properties and sustainable benefits of molybdenum, a key alloying element in stainless steel and nickel-based alloys, enhancing corrosion resistance in various modern applications. And now it gives me, of course, great pleasure to introduce to you Dr. Graham Sussex. Graham is an expert in corrosion and materials consulting with over 35 years of experience. Serving as a consultant for the Nickel Institute for more than a decade, he brings extensive knowledge in stainless steel applications and standards. He has also been a technical specialist with the Australian Stainless Steel Development Association for over 20 years. His active involvement in ASTM and Australian standard development has significantly contributed to the advancement in the Australian-New Zealand welding standards for stainless steel. And with that, I would like to hand over to you, Graham, and to everybody. Enjoy the topic, and I hope we will get a lot of questions. Thank you.
Host has disabled screen sharing.
Just a minute, just a minute. Yeah, please start, sir.
Yeah, Graham, you have the rights now.
That show up okay?
Yes, sir.
Yep.
Good.
Yeah, we can. Yeah.
Okay, thank you very much. I've shown 3 pictures of uses of duplex there. I'll talk about them in a moment or two, and they give you an indication of the sorts of places that it's used. These are the proposed content, which is basically the was on the flyer. One little different, well, it's actually disappointing for me, a difference. I just ran out of time, so there's not going to be very much about the cast duplex alloys at all, I'm afraid. Okay, talking about the pictures that I showed first, on the left, there was a super duplex welded tank for impure phosphoric acid. Lots of strength, lots of corrosion resistance, and in that particular case, it was a super duplex. In the center, the tank on a ship made out of 2205, very reasonable match of the thermal expansion with the carbon steel hull. A lot better than austenitics. And it's pretty strong, reasonably light, therefore, because it was thin. And it's got corrugations in it to give you lots more strength. Okay for near ambient temperature with chlorides if you were carrying things with chlorides in up to those sort of limits. And across to the right from a desalination plant, and you've probably all seen pictures of these before, pumps, vessels, pipe work, getting potable water, go in 2 steps usually, 20,000 milligrams per litre down to a few hundred, and then second stage down to ambient. And while you could use 316L for those, often people use 2205 because thinner walls and so on. There are 3 more families. The hyper-duplex grade, I don't have a picture of them because there's basically only one supplier at the moment. Seamless pipe and strip, and welding them can be quite difficult. The 2 lower grades, the low alloy ones, a bit more chrome and moly, better corrosion resistance than the leans. Not a lot of difference. You'll see that in a minute or two. Slightly lower strength, but pretty much easier to weld. Was used, incidentally, in the Hong Kong to mainland bridge reinforcement, but more commonly heat exchanger tubes, that sort of thing. The lean alloys, lower nickel, often more nitrogen, because otherwise it doesn't stay properly a duplex. And for getting the nitrogen in, often has higher levels of manganese than you normally expect. Lower cost, good strength, great for tanks. What's the advantages? You get benefits from ferritic and the austenitic properties because it's mixed. The mechanical properties, about twice the proof strength of austenitics. Strengthens up with cold work, but not as much as austenitics, so you can get a lot more strength, but you won't do the doubling, for instance, that you might get with an austenitic. Ductility and formability is quite good, but again, a bit less than the austenitics. And you can select the corrosion resistance. You basically put whatever alloy level you want, and you can measure it by the pitting resistance equivalent, and I'll talk about that in a moment or two. Very good against chlorides, printing, crevice, and particularly against cracking. You have to really work hard to make the duplexes crack, and some oil industry people, of course, do. Ferritics are going to be better. Very good in oxidizing environments like all stainlesses. High temperatures, well, not really. Structural up to about 315 C, although some people hold it to about 280. But you don't go putting in the high hundreds for a long time, and I don't mean hours, I mean minutes, because you get bad phases forming. That's something that can be a problem with welds, of course, and we'll talk about that in a few minutes. Low temperatures, minus 50 or so, nothing like the austenitics, of course, going down to absolute zero, minus 273.16. And the 0.16 is apparently very important. Embrittles with hydrogen, and it's less available than the austenitics. Austenitics, roughly about 70% in the world, and the ferritics, 20% or a bit more, and the duplexes have to fit in there. Quite good weldability, but it's a bit sensitive to time at temperature because of getting extra phases, and we'll talk about that. So, stainless steels, passive layer forms, you get moisture in the air, oxygen, nice thin layer, passive, and it's millionths of a millimetre thick, but it takes somewhere between 4 and 24 hours to reform. It doesn't happen instantly, so if you carefully brush the surface up and then put it into service immediately, you don't expect to get absolutely top-rate quality out of it. And what's in it? Chrome, moly, nitrogen, those give you corrosion resistance, and the nitrogen, nickel, and manganese give you your physical and mechanical properties. The amount of material that's in there, manganese I've put up to 11. That's only in some of the specials where you've really got to work at getting nitrogen in, because manganese does make it a bit easier. Pitting resistance equivalent, the formula you've probably all seen everywhere. The W is only for the tungsten versions that come out of the 0 and 100, that sort of stuff. But the rest has been around for a long while. It's, if you're looking at ferritics, and we're not usually, then you drop out the end term because basically you don't get nitrogen dissolving. And if it's more than about 40, then it'll stand up to seawater. There's nickel not in there. I've lost count of the number of times people say the nickel isn't good enough, therefore we're going to have bad corrosion resistance. It's not true. It simply selects what happens in terms of what the microstructure is. And this is a formula that was worked out for austenitics. It does work for ferritics. It does work for duplex, but it's only an approximation. And so if you get a variation of 1 or 2, then it may well not be critical, but it does work, as I say, for ferritics. Significant part of the corrosion resistance for duplex comes from the nitrogen, and particularly for the lower alloy ones. So quite often you will see a 30 instead of a 16, because it was found that if you just basically used that PRE and then compared it with a chemical test, you got a lot worse results from this PRE number, as in it said, no, it won't work, but it did work quite well. And that's basically just, if the nitrogen is up, then you put up a higher ratio. Body-centered cubic, ferrite, add nickel, and you wind up with face-centered cubic, weldable, formable, tough, and nitrogen is one of the things that help with that, making the structure. And if you add manganese, I've already said, it improves the nitrogen solubility. So that's ferritic on the edge. Add some nickel, but not a lot, and you get the duplexes, and I'll talk about that picture in a bit of time. And of course, if you go the whole way, then you get the austenitics across the far side. So just a bit of history. Sweden back in 1929. 357 tons of an alloy made in 1932, so a long time ago. And the early grades were neither low carbon nor alloyed with nitrogen. You had to wait until the 1970s when we got argon oxygen decarburization and control of gases to get reliable welding and to get good compositions. So I did the wrong thing. This was a vessel called a Brobeck cooler, 1932, fully annealed after welding. Interesting job, fully annealing that. In France, there was a duplex alloy made by accident in 1933, and through from about the 30s to the 60s, it was for non-welded applications, bars and forgings, cast components, seamless tubing, basically because you couldn't weld the stuff. There was no good control of the nitrogen in particular, and it was also a bit difficult controlling the carbon. So why does it solidify as duplex? This is a diagram out of Lippold on welding metallurgy and weldability. Good book, but it's quite heavy reading. And the band down the center is where the duplexes are. The line, the numbers across the bottom are typical alloys going across there. The metal solidifies as ferrite, solidifies as 100% ferrite, and then some of it's going to transform once it gets below about 975C, as it says there. It's a bit more complicated than that, and the actual number will depend on where you are across that band. Typically, you're aiming for about 50-50 ferrite austenite, but you can go quite a bit different and still get quite good results. If you get too high ferrite, though, you get poor low temperature toughness, pretty awful stress corrosion cracking from sulfides, poor corrosion resistance because of chromium nitrides forming, and probably lower tensiles. You get too high austenite, hey, fluoride stress corrosion cracking, here we come, and you'll get lower yield and tensile strength. Typically, you aim for ferrites of 40 to 60 in the base metal and 30 to 70 in the weld, a heat affected zone, but the closer you can get to 50-50, the better. One of the big problems, particularly with the higher alloys, is intermetallic phases. So instead of getting nice oxides on the surface, you wind up with iron, chromium, sometimes moly, and you'll lose ductility even at 20 degrees C. You'll also get pretty poor corrosion resistance. The insect in the ointment, I was going to say fly in the ointment, but I decided not to, but I did. So more chrome and moly, the faster these phases are going to form. Here we're looking at temperatures, and I hope you can see enough of that, looking at various areas. So we've got 2205 there with the solid lines, 2507 super duplex, and then one of the lean low in the other dotted lines, 2304, and the precipitates that happen. If you've got lots of nitrogen, it's going to happen less rapidly, but it's okay because all modern duplexes have nitrogen in them. So what have we got there? We've got nitrides. That particularly happens with getting too much ferrite. Carbides, usually not a problem because we're looking at pretty low carbon in all of the duplexes. And then down the bottom, we've got the reason why you don't go above about 315 if you're looking at structural, because you're getting the 475 degree embrittlement. And those two lines there are 50% loss of toughness on the right and hardness on the left. These graphs come straight out of a thing that I'm going to reference in IMOA publication. And 50%, I just said that. And I've already said that. This is a publication straight out of the IMOA fabrication of duplex stainless steels. It's still the 3rd edition. It's been it for a long while, and I've been told that the 4th edition is coming, but so is Christmas. Okay, so here we've got the low and lean ones, the 2101, 2304 across there, and look down the side and you see that we've got in the 20s for PRE. So it's better than 316, but it's not as good as full-scale duplex as in 2205. All have got low carbon, all have got added nitrogen, and mostly, as you can look down there and see, there's not terribly much nickel. The moly one's a bit better, bit higher corrosion resistance, but yes, that's the family. The standard ones, 2205 is the one that everybody knows. One thing that perhaps people should realise is the bit that the old 31803 is dual certified with 2205, and there's the compositions, and you can see why. Basically, the 2205 takes the top half of the corrosion resistance, the chromium, the moly, and the nitrogen, and you've got that sort of level of 35, 36 corrosion resistance PRE. Go down the bottom, and we're looking at super duplexes, and there are a lot of them, but the common ones, 2507 and 0 and 100, have got the PREs all greater than 40. There were, for a long while, things that were touted as super duplex because of the compositions, but in the standard, it didn't actually say that. And people foolishly were using things that were actually less than 40. Nowadays, most of them have a little thing in the remarks column saying PRE to be greater than 40 or 41 or sometimes 42. And right down the bottom, 2 grades and 1 supplier. And you're looking at 50 or more. Seamless pipe or seamless tube, sorry, or sheet. Well, not sheet, but plate. You don't, welding them is difficult, plain difficult. Whoops, what happened then? Okay, strength versus elongation. This is just to reinforce that ferritics, austenitic are less strong than the duplexes, and the martensitic's way up there. And I did mention earlier that the duplex has been drawn. These are pictures of austenitics, but you can actually get quite a bit of extra strength just by cold working the duplexes. What about the actual mechanicals, and what difference is there between ASTM and EN? And the short answer is not a lot. There are fiddling around the edges. but in terms of yield strength or 0.2% proof stress, tensile and elongation, not a lot of difference. The using it A5 or elongation in 2% is just language. One thing about it is that the EN standards tend to have narrower ranges than the ASTM. So if you're ordering to ordering to EN and somebody supplies to ASTM, you just need to have a look and make sure that it actually will still fit. And this is, I'm sorry, the only thing I've got about castings, and it's the same source. And take a look at the compositions down the side, and we've got duplex levels, we've got we've got super duplex levels as well. The bit that doesn't show up in the top row is the silicon, because silicon tends to be just part of the actual thing. I gather we're going to deal with questions at the end. And that's basically compositions. So the J's are just not used. Okay, testing standards for duplex. For flat products coming to ASTM A240, and I'm sorry, I do tend to run to the American standards, mechanical and chemicals, but some of the tests were written for austenitics, and some of them, A262, for instance, just don't work. 923 and 1084 work for duplexes, although 1084 typically is used for the low and lean, and 924 for the ones that get king hit. The 923, I did say that, I hope, are likely to have the highest amount of intermetallics because they're thicker, usually, slow cooling, and so you may well get intermetallics as you're welding them. It has criteria for welded products. It has been assumed in there that they're mill products, and so they've been heat treated after welding. If you have tests done after that, then, well, you really should do them after final heat treatment. I've got to say that that's observed more in the not doing it than in actually complying with it, but that's the way the rules work. 1084 for the low and lean alloys and doesn't refer to welded materials. The tests are slightly different, and I'll talk about them in a minute. As I say, they're sometimes used for shop welds, and nickel publication 10044 has been updated and considered both of these standards. It's from the number you'd think it's very old, but no, it's quite recent. So what's in them? Okay, it's specifically mentioned in 923, 2205, 255, and 3 of the super duplexes is wrought, and then the two cast alloys there. It detects detrimental amounts of any intermetallics. Yes, it's a matter of making the decision about just where you draw the line. And there are 3 tests, the metallographic, corrosion test, and impact tests. And they say that any one of the 3 is satisfactory. 1084, well, it specifically mentions those lean and low alloy ones, and it will detect detrimental phases, but the phases we're talking about are nitrides and carbides usually, because intermetallic phases, there just isn't enough high alloy in there to actually do that. Slightly different tests, but only one of the 3 is required to make it work. A lot of people do all 3 tests on both. One of the little problems is that it doesn't cover ferrite austenite, and you're supposed to be 50-50. And the impact tests aren't the same as in ASME 8. The pass-fail criteria for the corrosion tests are to look for detrimental phases, and it's not looking for a specific corrosion resistance, which may be set by the specific composition. So you may get away with having a certain amount of detrimental phases, and that rule may say no, but if you actually do a test, it may well be okay. If you do any heat treatment or heavy cold work afterwards, it negates the results completely. And where's the test piece from? Is it from the thickest bit or the thinnest bit, or is it near a weld? If it's in a place that's going to fail, then yeah, you need to be in the right place. There's an ISO 17781, which the oil and gas people use, and that basically works for all duplex stainless and puts them into 5 categories. So we've got 5 levels. It also has the ferrite levels, as well as detrimental phases. Specifies a lot more details about where you take it from, as in the thickest bit, at bends, near welds, etc. It will look at covering welds in the as-welded condition, as well as wrought cast, HIP, isostatically pressed, and it's a bit more specific and comprehensive about what you've got to put in the test result reports. You've got to report everything. It's not just pick one, but that's it. The Norsok, the Norwegians, commonly used in the North Sea, very good standards, but it is very tightly tied in with that. If you're looking for the ferrite-austenite ratio in wrought material, it's usually expressed as a percentage ferrite. That'll be 0.1 up to about 80, or a ferrite number, 0.1, sorry, up to 110. They're not the same. I'll give you an example of what it means. And you can do it several ways. ASTM 562, you take a wrought sample, you do a transverse direction to the rolling, polish it, etch it, put it under a microscope with a grid. That can be a circular grid or a square grid or whatever, and count the intersections. Yeah, with the particular phases that are there. You're going to need hundreds of points if you want to get lots of accuracy, very time consuming, very prone to operator error, and it's a destructive test and it's slow. Computer image analysis, great, easy. Well, yeah, except that you've got to do the cross section, you've got to etch it properly, then you make sure that it's a really good, clean preparation and etching, and then it'll be able to detect the phase or the feature of interest compared to the background. And that's often quite difficult. Or you can go for a magnetic technique, magnetic things, and you can get quite close to a weld and get good results from that. But it's not quite as accurate because it doesn't detect very small areas. You have to properly calibrate it, and it's not so good if you're measuring on a surface that's rough. And you can't measure small has separately from the weld, whereas you can with the point count. If you're looking at it, just some comments about that. If you're talking about high ferrite, okay, low ductility, loss of corrosion resistance, and cracking, hydrogen cracking. High austenite, low stress corrosion resistance, and usually low strength. And if you go, well, you can balance it and keep it in the middle. But if you're in balance, well, composition, high nickel and high nitrogen is to go to increase the austenite. If you want that, fine. Heat input, low heat input, likely to get excess ferrite because it'll cool down very quickly. It doesn't get time for the austenite to form. And cooling rates, if they're going down too slowly, then you'll get much too much austenite. Too fast, too much ferrite. Said that. And in the middle, you get the intermetallics. So this is what a weld looks like. And this is a picture I swiped from Sandvik, I think. Across to the right, we've got the weld material cold rolled. In the middle, we've got the actual weld, cold rolled the plate. And then on the left, we've got a real mess, which is in the weld metal. And it's going to look like that anyway. What accuracy do you want to do your measurements on that? Well, imagine that you're putting down a grid on that. How do you space it so that you don't wind up with lots of zeros in it if you're looking in the middle or even on the left? You have to basically do some sums. ASTM 526 has got some quite good data on that. Gives you what accuracy you want, and they suggest looking at either a third or a tenth or 5%. And that really makes some assumptions about what phase you're interested in. So are you going to have a square grid, a round grid, whatever? because you do want to make sure that you don't go intersecting multiples. And if you do hard work to get a heavily worked martensite, you may contribute. So if you're using a ferrite meter, you'll get a number. And the third phases, or lousy polishing, is going to give you errors, especially if you're doing computerized image analysis. They recommend at least 400 times 400. Well, the problem with times 400 is that in a HAZ, that may be too much. And if you're right in the middle of the weld, then how do you just look at the weld? You can measure it other ways. You can use a ferrite scope. I said that before. It'll give you units designed for welds in austenitic alloys, not in duplex alloys. Right. So there is a calibrated ferrite number used in the Welding Research Council 1992 graph for designing consumables, and it can sample quite small areas. I mean, you look at the size of the sample and it's less than a centimetre. Or you can directly measure the force required to get a magnet off it by a magnetoscope. Bit of an issue with standoff there and shape of the surface, but still it is recognised, not commonly used. Ferrite scopes are much more commonly used. Or if you're looking at really low levels, use a pull-off gauge, but that's old history for the days when you were looking for levels of ferrite in austenitic stainless steels. This is the Welding Research Council, not WTC. Gosh, sorry. There's bound to be some things. 1992 ferrite number. And it is not the same as the Schaeffler-DeLong weighting, especially for silicon. But on this thing, we're looking at numbers across the bottom, the nickel equivalent and the chromium equivalent, and then what's going to happen. And on this are the ferrite numbers going across there, and the percentages are going to be different. And this is where we've got the lean and light, ordinary duplex, and super duplexes. And these A, AF, FA, and F are simply saying out here it will solidify as austenite, there it will solidify as austenite with some ferrite, here it'll go as ferrite with some austenite, and here it's going to be all ferrite, except it doesn't work quite that way because of where these alloys are. So let's do some conversions. If you're looking for a ferrite number of 16, then that's about 13.8% ferrite. If it's 100, that's about 65% ferrite. And for very low ferrite numbers, up to about 8 ferrite number, then the ferrite is approximately the same. And here's the ferrite numbers across there. Okay, why do you get weld failures? Well, incorrect design, thickness versus loading, weld dimensions, joint restraint, wrong weld procedures. They're experienced people working into a new area. So somebody who's used to welding austenites and moves across to duplex, heat input, interpass temperature differences, because interpass temperatures for the austenites tend to be not nearly as sensitive. Excessive stress raises, well, that's all over the place because you rise the fatigue risks. Poor welding, contamination, rough ground surfaces, lack of root penetration or fusion. That never happens, does it? The welding's always good. Undercut, overroll, slag inclusions, gas pours. Got to say, people worry about gas pours all over the place, but unless they're due to water and you wind up with a whole cluster of them, then it's usually not too serious. And other stress rises, just not following the weld procedures. The major extra issue with duplex is just the sensitivity of the heat input. Put too much heat in, keep it too hot too long, and you'll muck up the actual solidification and you'll wind up with wrong ferrite austenites. And looking at intermetallics, the higher the chrome and moly, the quicker they're going to actually go. And they're going to remove support of the protective oxide film that's on the surface, and quite possibly embrittle because they come out, and when you get down to room temperature, they will just embrittle and crack. They also take away because they take away the protective oxide, then you may actually just wind up with corrosion. If you're putting nitrogen in, that happens with the low alloys, then it slows down the formation of the intermetallic phases. But the early duplex alloys, no nitrogen control, and so they really didn't know where they were. And so they were very prone to both high ferrite and the formation of the intermetallic phases that you really don't want. This was an expensive thing. I've put in the name of the alloy, which is perhaps a bit unfair, but this was pieces of pipe. The contractors were a bit rough and ready. The bit on the left was welded and then weld repaired, and I gather in some cases weld repaired twice. And then they were put into seawater, yeah. And they wound up with corrosion, as in leaks, right next door to the weld because at the top it cut off. And that sort of thing happened. The one on the right was after they had done proper welding, as in low levels feed input. It's gone through the same G48 test, but there's no sensitization. So across that band at that level distance, you've got intermetallic phases forming, and it just corrodes quite rapidly. And it was sigma phase. I've seen test things where you put 20% or so of sigma in there and then heat treat it, goes away and it's beautiful. But of course, people don't do that if they're building stuff on the site. Okay, what about rapid cooling? Rapid cooling, the obvious place is arc strikes. Well, arc strikes never happen on the surface, do they? They always happen in the weld or on a starter tap. I hear hollow laughter through the ether. If you've got a small arc strike, it's basically a splat cooled on a very large heat sink, and it's almost pure ferrite. And so it'll cool down, and it'll cool down until it's too low for the austenite to nucleate and grow. And what happens to the nitrogen that was in the ferrite? Mind you, there's not there. And it just, I've got that the wrong way around. Huh. Yeah, okay. There's no austenite to actually take up the nitrogen. And so the ferrite precipitates out, the nitrogen combines with it, and you wind up with chromium nitride. Chromium nitride tied up with the chromium tied up with the nitride means that you've got less corrosion resistance. And so you wind up with a problem. Typically, if you look at an arc strike, it's got big grains of ferrite, traces of austenite on the grain boundaries, and that's about it. The ferrite doesn't have much in the way of nitrides, but right up close, beside the austenite, it's okay. But if you go away from the austenite, then it's loaded up with chromium nitrides, and the surrounding zone is depleted of chromium simply because the chromium has taken up, the nitrides have taken out the chromium. And so instead of being chromium oxide, it's chromium nitride. And here's the sums. Cr2n, true chromium atoms per atom of nitrogen. So you get a chromium depleted and corrosion susceptible zone. And 7.4 times the mass of chromium. I thought I'd put in the sums just to get some idea of just how bad it is. And chromium nitride is actually quite large and quite slow to diffuse, so it stays put right next door in the lower PRE. And it'll pit. And people have done the experiment, and you need to go down almost a millimetre in depth to get away from the zone where it's needs to be well repaired. Lessons: no untreated arc strikes, and for the same reason, no autogenous welding. Right. What do we want in a welding process? Slow cooling to about 1,000 degrees to allow the austenite to form, and then a fast cool to about 550 to avoid the intermetallics. Well, you can't exactly specify that, but you can say it. But the heat input is just that, divide by the travel speed and the duty cycle of its pulse shape. That's not actually, it's an experience thing, and you write the procedure that will actually do it. You're going to allow for the thickness, the dilution, the parent metal temperature. If it's all cold, it's going to cool quickly, and the efficiency of the weld process, how much energy you're putting in and how it's getting transferred. And for duplex, you've got to give a maximum, and I'll show you a picture of it in a minute, but also you've got to give a minimum, because otherwise it cools down too quickly and you don't wind up with proper formation of the two phases. Typical for 2205, about 0.5 to about 2.5 kilojoule per millimetre. May be you can get to a lower minimum if you're using a laser or laser hybrid welds, because you're not putting quite so much heat in. But you wouldn't use autogenous because the heat input's going to be too low and because any nitrogen will just go away. Specifically, let's look at the interpass temperature. Typically, you're looking at about 150 to 250. And yes, I know they vary a bit. If it's too high, then slow cooling and into metallics, maybe distortion if you really cook it. And what do? Well, heat treatment. Yeah, you might preheat it, but really it's only just to warm it and dry it out. Or if you're talking about a really thick section, yes, okay, you may have to preheat it. I'll talk about that in a moment when we talk about this REAC example. And afterwards, then it's not usually, I mean, it's much the same as looking at L-grade austenitics, because post-weld heat treatment for getting rid of carbides, you don't have an issue with it. A full anneal and quench is just a bit of a risk. So this is some diagram I swiped from AS/NZS 1554. Oops, sorry, it's AS 1554 Part 6 these days. Arc energy input against interpass preheat temperatures. So for a fully austenitic, something that's going to crack if you even blink at it, keep the temperature down 0.5 to 1. You've got to have enough for fusion, obviously. Austenitics, standard austenitics 304, 316, yep, up to there. Duplexes, you can go a lot further, out to here. And if you're going to the super duplex, then you've got to come back here because you don't want to have too hot and too high for too long. I like that diagram. It's something that came from somebody who worked for Sandvik. Low interpass temperatures to avoid, yes. One little complication is if you're swapping from one metal to another, then look about what happens with more nickel or less nickel. So mild steel and 12 chromes, lots of penetration because there's very little nickel. 304, 2507, 2205, same sort of band, that much penetration. And the really high nickels, not much penetration at all. And higher nickel also makes a more viscous weld pool. So increasing the current won't speed up the welding no matter what you do. You just get too much heat in, you'll get it too hot, and then you'll wind up with other problems. This is a cross section. Here we're looking at a cold rolled piece of material, ferritic from where it actually originally solidified, and the austenite has grown out and then been rolled out flat like this. And unfortunately, at the grain boundaries, because there was a bit of a problem somewhere, you've got sigma phase forming, these little black specks. There's not the hell of a lot of it, and that may actually be not enough to worry about, but it's something that would be picked up and reported. Yes, I've already said sigma is brittle, low corrosion resistant. All right, so assessment of the weld metal has. In the weld metal, it's a mixture of the filler, the base metal, whatever nitrogen has got taken off from the weld pool. And if your shielding gas has got nitrogen in it, or if you're welding in a pipe and you've got purge gas with nitrogen in it, then you'll get nitrogen taken up and that will help to give you austenite. Time and temperature, it's going to be a function of the cooling rate plus heat from any multiple passes. And I'll show you an example of that from American Welding Journal. It's quite interesting. Each pass will get different thermal history, and you'll get the percentage ferrite changing and different intermetallic phases. The heat affected zone, the composition won't change all that much, but the thermal cycle means that you may get intermetallic phases and a bit of a change of the austenite ferrite as well. And if you're trying to assess production welds, how do you do it? Well, you could use a ferrite meter, but not easily do anything else in terms of getting ferrite austenite. Okay, what are the Has properties? Well, you can specify things, the ferrite range, maximum and minimum, but how big is the Has zone and how are you measuring it? Intermetallic phases, well, okay, yes, you're just going to have to look at it. A pitting corrosion test, yes, use different temperatures for different gauges and they're set out in the standards. And low temperature toughness, V-notch -40, possibly -20 if you are not going down a long way, but a lot of standards just say -40 and that's it. And hardness less than the maximum, yeah, that's not usually an issue. And 0.2% proof and the tensile strength. And I really don't like people talking about 0.2% yield because it's a stainless steel. It all cold works. Okay, what about joint parameters? How do you put it together? This is again lifted straight out of the IMOA Nickel Institute publication, looking at, compared to 316, a wider, perhaps 10 degrees wider root gap, slightly smaller land, the bottom to retain the stuff, just to think about the nickel content, and it's sluggish, so you don't want to have it not going through there. You actually want to get it through, otherwise you wind up with lack of penetration. And this is just a series of recommendations. And weld prep. Grinding, perhaps not. You want the surface nice and clean, nice and smooth, and you want it clean. A non-residual solvent clean at the end, not anything that's going to stay there and can be detected. Okay, same processes as for austenitics. Lower heat input, not recommended. So if you're using laser or resistance welding, well, if they need nitrogen at the upper end, yes, that would work. Resistance welding, yeah, okay. How do you avoid well, yes, you can flood it with nitrogen. Laser welding has been used for T and I structural beam, putting a nickel foil in it, but it was a bit of a mess. Sorry, not a bit of a mess, but it was a difficult process, so it tends not to be used now. And GTAW without a fillet is not allowed unless you're going to anneal it, because low kilojoules, possible nitrogen loss, and so your phase balance would be an issue. Most reliable process for heavy plate, submerged arc. If you're welding in the flat position, and when a proper flux is used, perhaps even a chromium compensator one, but you need to actually know what you're doing with it. Shorter metal arc, nominally matching filler metals. Unfortunately, they're usually over-alloyed with nickel, which is all very well, but as it cools down, you're going to get lots and lots of ferrite taken away, as low as 25%. And that's getting to the bottom end of what you can actually get and still call it a duplex. So you may be better off just accepting the recommended matching filler metals. Certainly if you're doing weld repair on castings, you would be full annealing. And so you'd have to match it up fairly nicely. GMAW, as with austenitic, can use short circuit, pulsed arc, spray mode, and gas is appropriate. not common to use nitrogen, and the weld profile tends not to be as smooth as for austenitics. I think I'd go stronger than that, but still. Flux cord, common, using 100% CO2 or argon CO2 mixes. There has been a problem with getting decent sharpened V-notch impact properties. The impact test in 923 uses -40, and if the item can be used at -20, then hey, the weld may be suitable, but it's a thing that's known and needs to be carefully looked at. GTAW or TIG, nitrogen the torch gas, yeah, that'll help, 1 to 5%. Purge gas, if you're looking at a piece of pipe, you always have purge gas, and hey, it always helps if you've got it, because the root is going to be the thing that is absolutely likely to get most corrosion problems. And so you put some nitrogen in. You can use formula gas. The hydrogen will take out any heat tint if you've got a bit of oxygen around. Formula to nitrogen to argon plus nitrogen. Largely, people are going to use all nitrogen. You really don't go doing wash passes because you're just going to get the thing warm enough, probably to cause problems, without actually doing much in there. And if you're doing repair welds, then do you actually get the filler metal to the repair? And it's low heat, so have you actually got enough heat in to get proper austenite content to form before solidification? Because remember, it's solid, comes down as a ferrite, and then it has to cool slow enough so that below 1,000, so that you actually form the austenite. Filler metals, E or ER, so electrodes or rods. Filler for 2205 with about 4% over nickel. 2307, very similar to 2304, but about 3% enriched with nickel. And make sure that you've got upper end of the nitrogen to make sure you get enough austenite, because you can't put too much nickel in there, because otherwise you'll move up into the next range. And for super duplexes in 0 and 100, or both super duplexes, 2% nickel. And all of these, extra nickel, just to make sure you get the austenite from them. And look, other filler metals you can use, but you just think about how much austenite you're going to form. And for the lean and low alloys, there are so many alloys. You saw how many there were. It's much better to use the manufacturer's data for the best guide. People often use 2209, lots and lots of nickel in that, but you wouldn't use that if you worry about moly because of detrimental to the specific surface. I didn't know about this until I looked it up, but there's some research around suggesting that in alkali chloride, there may be an issue with that. So, but it's very specific to particular environments, acids they're forming. Submerged arc, then 2209, your wire needs to have pretty high nitrogen content to match the strength levels, because otherwise you won't have enough. Minimum heat input, generally given 0.5 kilojoules per millimeter, but can be lower, provided you have got enough heat in there to actually get the solidification properly. And maximum heat input for the lean and low alloy generally is going to be lower. And here's a bundle of suggestions, just straight out of the texts, looking at the alloys there and the electrodes or electrode rod choices. 2205, standard fill is 2209, but if you're welding that rather than 31803, so you're up in the top end of the range, then look at the high end chromium, moly, and getting at the high end there. So you do have more corrosion resistance in the system, but 2209 has just got 22 chrome. and maybe you need to be looking at a bit more nitrogen. Sometimes super duplex root weld, but you need to be careful. You need to make a similar size weld for the root and second pass because the super alloy is stronger. And that means you'd have, if you just had the root, the super duplex, then you've got something close to the inside, which is not as strong. So 2 passes and then go back. And unfortunately, new welders and supervisors may not be as familiar with duplex. I mean, people typically go carbon to austenitic to duplex, and particularly worrying about heat input, shielding and purging, if you're talking about tubes and pipes. Welding super duplex, high end of composition, just because, hey, you're looking at something that's going into a very aggressive environment and you're going to lose some of the consumable at the actual welding process. Lower heat inputs at 2205. Yeah, something I'd like about that. If you're talking about submerged arc, then you can often go up higher. Low interpass temperatures because you don't want to keep it too hot for too long. And you'll get some intermetallics in the super duplexes, but it's not going to be a problem unless there was a problem already, and then you've got a problem, and then you're doing another weld, and you're likely to have a similar problem, and you'll be doing it, chasing your tail. All the super alloys weld okay, but sometimes there can be application with tungsten or copper additions, copper because of acid resistance and tungsten because the particular company that does it, uses it and gets very good results. Using nitrogen shielding and backing gases is more important with the super duplexes because they've got higher nitrogen and you're going to lose it from the weld pool. And you can weld with the nickel base at 625, but lower strength, and you're likely to get niobium nitride precipitates. And for those of you who think back to nitric acid and 316, 304, 304 usually, pardon me, you get titanium nitride and knife line attack, which is not nice. Okay, now this comes from the American Welding Journal, and it's looking at going down the page, a weld there, and you've got 43% austenite. Second phase in the root, 49%. Third phase, you've got 55%. And right down the bottom, I can't see it, damn it. How do I get rid of that? Move that up to the top. Let's try going. Put it up there. Yeah, okay. We're at 53%. Why? Well, you can see the difference in austenite. And the reason for it multiple heat cycles after solidification. So every time you get up into the heat cycle, then you're reforming. Bingo. Okay. This is as welded and changing the gases. 100% argon, 35% austenite, 98% argon, 37, and 94% argon, 42 austenite. Why? Because the other thing that's there is nitrogen, and nitrogen is austenite forming. And here we've got, yes, 63 kilojoules per inch, 78.3 kilojoules per inch. The Americans will love that. And massively different amounts of austenite. Why? Well, look at what's in there. More heat, larger weld pool, lower average nickel in the weld pool, plus longer time as liquid weld pool, because more power, so the nitrogen can escape. So you get less austenite forming, gives less austenite. The things you find when you delve into a weld. Okay, now we're looking at ferrite balances. Filler composition, what heat input is there, and the cooling rate for thin materials, especially if you're going against a thicker plate. And don't forget about people who are trying to get through very quickly and putting lots of heat in and going, because they're paid per the item. Dilution, the nickel content, loss of nitrogen from the weld pool. I've just shown you the example of that. Nitrogen, the shielding gas, put nitrogen in the purge gas. And effectively root passes, the later passes on the root run shown in the previous slides. Nitrogen's improving the austenite reformation in duplex steel. That's almost a tautology. You're aiming for 30 to 70% volume ferrite, but you really want it nearer to 50-50. And shielding gas, 1 to 2.5 when you TIG welding. Purge gas, you can lose 50% of the ferrite in the root run. That's not all that good. And conversely, drop it down by 0.05 and the ferrite will go up by 10 to 15%. So it's actually a fairly delicate balancing act, and you actually need to think about it. But that's usually the person who's actually the welding engineer who's done the design. And the Formia gas reduces the heat tint. The hydrogen won't get into the arc because it's on the inside, and continue the purge until you've got at least 6 millimeters of the weld deposited if you're talking about a thick material. I have told the story to people of some people making pipework for desalination plants, good thick stuff. And they did the first 2 passes and then turned off the purge gas, and the inside of the things were absolutely black, which was lots and lots of cleaning. Okay, so what's happening here? We saw this picture before. Sigma phase forming up there. We're cooling down fast, slowly. Oh dear. Down there we wind up with sigma phase. Not good. We'll also wind up with a problem with the alpha prime. I did say before that at the bottom here, we've got 50% change at these for toughness and hardness. So let's cool it fast. Oops, that's much too fast. Excess ferrite. No, not good. And that's about right. So it's like Goldilocks and the Three Bears, for those of you who had Enid Blyton stories. And I've said before, modern duplex, low carbon, so carbide precipitate is not usually a problem. This is the thermal thicket. Chromium nitrides on one side, intermetallics on the other, high ferrite on the left, high austenite on the right. And you wind up with that sort of microstructure. And the black dots in the high austenite side are intermetallics. There aren't a lot of them there that probably would pass, but it's not good. Okay, this is a failure investigation at a reactor effluent air cooler. And there was duplex 2205 being welded, sulfide stress cracking because high ferrite, high hardness weld root, because it was welded to something that was relatively thick and it didn't give you adequate heat. And so you wound up with a problem and a big fire. And leaks. Wow. All right. What happens when you do arc welding? It's local heat treatment. I'm sorry, I'm getting close to the time. I'm also getting close to the end. You're going to heat treat the thing. So one's the parent metal. Two's you're getting heat affected zone will get lower tensile strength after the welding, but not a lot of difference unless you're right next to the fusion line. I mean, people worry about it. I'd worry more about getting the stiffness because of the weld metal, but yeah, it's a point. Capping passes on the top, they're different. And you've got possibly problems at 0.3, oh, that's the fusion line, and then fill lines and the root pass. And they're all different weld structures, all different temperatures, and all you need to be thinking about what's happening, or the designer of the weld procedure. So this area around the heated thing is less corrosion resistant, the heat tint we've got, unless you treat it, either abrade it or electropolish it or chemically pickle it to remove the heat tint. If you're going to mechanically abrade it, then don't get it too rough, because there is a strong correlation between corrosion and surface roughness, and the break point is about 0.5 micrometer RA. Here's what happens if you put too much heat in. You should have a weld bead down the bottom, probably is the easiest one here, where we're talking about 4 millimeter should be right, and so the has on the back is okay. You do a lot faster, a lot thicker one, 7 millimeter fillet instead of 3.5, and you get an enormous area. And so you have to worry, you've got to worry about the backside, but also you've got to worry about how far the heat tint spreads up. This is the AWS standard. It was done for food, but it works perfectly well for ordinary corrosion resistance. And down in the green bit on the left, you get that level of heat tint corresponding at 3 to about 40 or 50 parts per million of oxygen. And they basically did it by running gas through with levels of oxygen and then did welds around the outside. Talk to the bloke who did it. No more than pale straw. Can be used as a guide. The European hygienic designers people, food people, have about the same, except they have a lot finer degradation, changes in oxygen level. The weld discoloration on the inside, according to AWSD 18.1, 2009, and yay, Australian ASNZS 1554 part 6, 1994. But that's basically came from Sandvik, so perhaps it's just Sandvik. And similar results for Duplex. So there you are. That's the level of oxygen you can afford to have. This is welding, manual 2507 weld, less than 25 parts per million oxygen, actually 22.7 on the left. And this is an orbital European hygienic engineering design guide, which beautiful in 316. So what are you going to do? Transport, storage, handling. You don't get carbon steel on it. You all know that. Sulfur. Well, don't think about that, but EP oils have lots of sulfur. Grease. Yep, same stuff. Chlorides from pens or from the environment. Low melting point metals. People who ask about welding stainless steel to galvanized should shoot the buggers. Still. Areas affected by cutting usually have to be dressed up, especially if they've been heated, plasma cutting, or lesser extent laser cutting because of the lower heat input and the nitrogen gas purge, which is basically used for blowing the metal away. And you need dedicated tooling and working spaces. Heat input and interpass, talked about it. Tack welds do matter for Duplex. Should be more frequent because it's stronger, frequent and longer than an austenite, but you've got to grind them out. You can't just leave them there. Hydrotest water has chloride limits. Typically, people talk about 200 parts per million, but sometimes that's too much. And adverse weather warnings about loss of gas shielding. So how do you clean up? Well, you can blast with glass beads. It's not going to go very far. You can grind. That's quite common. Wire brushes maybe, but don't go overheating it. And don't go going more than 0.5 micrometer. Or you can pickle it, nitric hydrofluoric. People don't like that. People like using things like TIG brushes where you use an electric current. It's slower, and it usually gets given to the apprentice who doesn't quite understand about how long he's got to do it for. Electropolishing or electrocleaning, this is the TIG brush that I was talking about. Both of those will slightly smooth the surface and give you a very bright surface too. And the little stars up there, if you've got a rough surface, you may need to post-abrasion passivate it That's passivate nitric rather than passivate and pickle. Or maybe you have to pickle it because you've got to get rid of debris. And if you've got a weld and it's got darker than pale straw, then you've got to clean it. You must, otherwise you're asking for trouble. And as you go down there, sorry, I'll put that in, you get better results. And the proof of technique that you're going to use may actually require potential measurements, or you put it in an Auger spectroscopy and hit it with a beam of ions and measure the thickness of the oxide film, which people can do. It's a bit expensive, but you can prove a technique that way. And that's it. Thank you. Any questions? Let's move this thing down. Oh, can I just...
There are Q&A. Some questions are there. If possible, you can answer it.
Q&A. Oh God, we've got Q&A. Well, Jörg, are you going to read them out, or is somebody else going to read them out?
Yeah, we can do that. But you have it open as well, the Q&A?
I've got Q&A, yeah. When an impact test is applicable for duplex and super duplex stain, what is the acceptance criteria? First question, I can't answer it. How can we respond to these later? Can we send them back to IIW?
I'm pretty sure, yes, we can do that. Yes.
Okay.
Krishnan will give you all the questions afterwards, and then they can distribute it back to the respective person. Yes.
Okay. Is duplex compatible?
We can do that.
Is duplex compatible with phenolic water? I'm not sure quite what you mean by phenolic, as in traces of, or, and could somebody just clarify that a bit? I'll keep going. What considerations are considered during welding 70 millimeter? Wow. Well, you're going to wind up with a lot of heat input. You need to really look at keeping your overall interpass temperatures down. Otherwise, you're going to wind up with intermetallic phases. And it's really, yeah, control it and keep the interpass temperatures down, which means it's going to be a bit slow. What may go wrong? I'm not sure what that question. What may go wrong? That question I can't answer because I don't know.
That's the follow-up of the just previous. What
Oh,
are the
okay,
precautions?
that may go wrong. Okay, if you if your temperature stays up for too long, then you'll wind up with intermetallics. So you need to keep the interpass temperatures down, which will make it slow, I'm afraid. Any special requirements for shielding backing gas? Well, no oxygen in it. And it depends. I mean, if you're using argon, then you just use it. If you're using nitrogen, then it will be cheaper, but you've got an issue that you may well take up nitrogen and you'll wind up with more austenite than you really want. So argon, I know it's more expensive, but that's foolproof. Gary, feel free to jump in and say, hey, he's wrong. Whether any of the technical talks presentations will be shared to participants, I've provided a PDF of the presentation to Jörg, and I imagine he'll pass it on to IIW.
Yes, that will happen.
Yeah, okay. Oh, why impact test temperatures -46 for duplex and super duplex, but for austenitics at -196? Because duplexes do not like temperatures below about -50. they've got ferrite in them, and the ferrite won't cope very well with that. So the impacts, yeah, that's it. Whereas austenitics can go down to minus 273, down to absolute zero. The question, ASTM A923 helps in ferrite number. We do as per ASTM 562, which is, oh yeah, sure, no problem. I mean, that's what the thing is based on. It's just, I hate to say it, but the Welding Institute did a whole series of tests 15 or 20 years, oh, it was more than that, might have been 25 years ago, and found that with doing point counts, then you find an error of 6 to 10, even if you're being very careful. It was around the actual proper number, but just, wow, it was not good. I don't know what duplex clad versus complete duplex. How popular are duplex clad carbon steel constructions? Are duplex clad plates easy to fabricate as austenitic stainless steel clad carbon steels? I've come across queries, however, found in the end of the day, it's better to stick to complete full duplex construction instead of duplex clad construction. What's your opinion on this issue? It is easier to deal with a full duplex, it's just more expensive. The people who do clad piping, I won't mention the brand name, perhaps Jörg, they mechanically expand it and then seal it at the end. Look, any clad material, you've got to then worry about every joint, and you've got to be careful about how the joints are done and make sure that everything's there. If you're doing a full duplex, then you've got corrosion resistance inside and out, and you don't have to worry about cladding issues. After cold forming of dish ends, what is heat treatment as PFHT? I'm sorry, can you answer that, Gary? Or I'll answer it later.
Yeah, I'm just wondering if it's PWHT.
Post-weld heat treatment.
Yeah.
Yeah, that would probably be it.
But yeah, it's a full anneal you need to do.
Yeah. Okay.
Not a low temperature anneal, but the full anneal as you would do on the plate.
Yeah. How are surface roughness and corrosion resistance are related? Yeah, okay. Basically, it's set out in EN 10088.2 as the difference between a 2J and a 2K finish. And a 2J is just an abraded number 4 finish, if you're talking about ASTM. And a 2K is one where the surface is no rougher than 0.5 micrometer RA, and the profile is regular, smooth, so there aren't bits sticking up. The reason why it's important is if you look at a magnified image of something that's been polished, particularly if it's been heavily polished, you'll see all tiny little bits of metal that have been torn off the surface and partly sticking. And so you've got lots of little crevices in there. And also, if you've got a very rough surface, then you've got deep grooves. When I say deep, I'm talking micrometers or less than micrometers. But that's something that can gather corrosives and cause corrosion. So the 0.5 micrometer is accepted in Europe, and we do it in Australia. This Stainless Steel Association in Australia has been pounding it for 25, 30 years. Duplex casting. What if we do welding and then follow the heat treatment process as required by the standard? Well, yes, that's what you would do. I mean, you'd have to do welding. You're going to have to do an anneal of that weld area. Otherwise, hey, it's just a problem.
Graham, I wonder if they're actually referring to the fact with the higher nickel, the filler metals, and what happens when you anneal it at standard annealing temperatures, and probably you end up with more austenite than you might be allowed.
Yeah, I don't know what the question was then in that case. Perhaps Tosif, if you could come back with a bit more detail. In case of desalination saltwater plant, how to control the corrosion rate, especially in cast welded parts, pitting and crevice found severe in the environment. I hate to say it, but I think if they're cast materials, I would get somebody to do either cut a sample out or do a surface replica and just see what there is in the way of intermetallic precipitates. There was a desal plant I was at where the cast bits had not been properly heat treated, and there was very, very rapid corrosion, and they wound up putting in painted, coated, sort of epoxy coated material, and it worked beautifully. The trouble was it wasn't as per design, so the things had to be pulled out and they put in stuff that had been properly heat treated. But I would think that would be the problem. I don't know what the surface roughness is, but I don't think that's likely to be a severe problem, because if it's significant corrosion, yeah, you're saying severe corrosion. No, I would think that's what it is. What's the reason for white patches appearing in duplex weld overlays using ER 2209 after pickling? It appeared only after pickling. Is the surface rough? How thoroughly? Oh, okay. Pickling. What strength of pickling was done? I mean, you don't need enormous levels, and it's usually that it hasn't been properly rinsed. I'm sorry for pointing the finger at your work, but that's one thing. I suppose the other thing is you could try doing a nitric wash of it afterwards. That's something that has to be done if you're looking at electropolishing, because you get some fairly resistant residual films. But it's usually just a wash to get the excess acid off and not splash it everywhere, and then a high pressure wash to actually get the last of all the acid off the surface. That's probably the easiest way to do it before you start mucking around with trying any further surface cleaning. Yeah, we've had that question before. Why impact at -46 for duplex and -196 for austenitics? It's just that the duplexes lie down and die if you go below about -50 or 60. Can we use higher diameter 4mm filler wire with SAW? Does it affect impact properties? I don't see that it would. I mean, you've got to melt the wire. Gary, any thoughts?
Yeah, I think if you're welding, like the person that was welding the 70mm thick pipe there, yeah, I mean that's certainly possible. You prove the fact that it works by doing your welding procedure and all the tests afterwards. But I've heard of 4mm diameter wire being used for subarc welding. Yeah.
Yeah, okay. Well, post-weld heat treatment required on duplex castings? Yes, quite definitely. What if we used 100% nitrogen for shielding gas? Well, you're going to wind up with your shielding gas. You're going to wind up with too much austenite. Not good. I think further back in the presentation, there was several different suggestions of things. And look, the fabrication of Duplex stainless steel 3rd edition, promised 4th edition to come since 2013. Sorry, I shouldn't be rude. But 100% nitrogen, no, not for a shielding gas. For a purging gas, yeah, sure. You're looking at one go. Argon 2% nitrogen. Both shielding and purging gas are required to be argon nitrogen. What? Well, argon, 2% nitrogen. Look, the 2% nitrogen is going to give you a bit more austenite, and the argon is doing your shielding. Yeah, I don't see any problem with that. What is the corrosion test failure in the 923, the Duplex 2205, even after precise control? Oh, God. Sorry, are we getting overrunning time too much? No. How many more have we got?
Yeah. You see, there are so many questions. We could go on for another hour, but I have seen as well, there are quite a number of people already leaving. So
Yeah.
just in case to the audience, the Nickel Institute has a very efficient, good tool. It's called Technical Help. If you go actually onto our webpage, www.nickelinstitute.org, immediately on the front page, you will see a yellow banner, Technical Help. If you go on that, you can register and then send in your question. This is all free of charge. And then it will be sent to the respective consultant of the Nickel Institute, and you will get an answer within 24 to 48 hours. So in case you have a question or you send in a question that did not get answered, maybe as well after the webinar in a week's time, you actually please use this form on our webpage. That helps us as well to monitor the kind of questions that are coming out and in throughout the world. So please use that. It's really free of charge, and you get the perfect answer from our consultants.
Jag, in addition, we will also compile all these questions, which will be sent to you, and then you can get it done between Graham and Gary.
Okay, thank you.
Yeah.
God, it goes
Absolutely,
on and on.
yes.
Yeah. All right.
Yes,
well,
and there are as well many questions in the chat box. So
Yeah,
it's
I think,
not only the Q&A.
yeah,
In the chat box, we have a lot.
Maybe Gary and Graham can write a book on this question. So many.
Yes, absolutely.
Is the Nickel Institute going to pay for it?
Yeah. So Jerk to answer.
Krishna won't answer that question to you, Graham.
I wasn't expecting it. It was a light-hearted comment.
Yeah.
See, this is one topic, the stainless steel duplex, super duplex, and this nickel in general. You get a lot of questions in the.
Yeah. Okay.
And,
well.
Yeah, and each question is unique. Yeah.
Send them all through. Yeah. Okay. That's it. Thank you, people. I hope it was helpful.
Absolutely
Yeah, so,
fantastic, Graham. So I give over to you, Krishnan, for the farewell.
So, thanks a lot to Graham for this fantastic presentation. I think the number of questions which raised shows, the interest from the audience. And thanks to Gary for joining us. This has been his early morning. Yeah. And
You're
also
welcome.
Jerk. Yeah. And also to Jerk for coordinating it so well. And thanks to all the participants who has been with us for the last more than 1.5 hours. So looking forward for the next one. I think it's from Gary.
Yep.
Yes. Yeah. It's from Gary. And the one after is from me. So, yeah.
Okay,
Okay.
thank you. Thank you all. Yeah.
Thank you.
Thanks
you.
to everybody throughout the world. Thanks.
Thank you.
Thank
Yeah.
you.
Thank you.
Thank-
Thank you. Yeah. Bye.